Okay, so we can start lecture number 2. Thank you for staying with me after the lunch. I will try to make sure that you don't fall asleep. Again, remind you can ask me any question, and we can talk after the lecture if you want one-on-one, whatever. Okay, so we're continuing our lectures on stochasticity in chemical and biological processes, and right now we will talk about some chemical kinetics, macroscopic chemical kinetics, and some phenomenological ratios. So this is a slide from a previous lectures. We learned with you that the stochastic effects are important for understanding chemical processes. Remember, I talked about the chemical reaction rates are random. Right? So stochasticity is important, and it should be important also for biology, because biology is a lot of chemical reactions. Somehow, many biological systems are able to tune stochastic effects to optimize the function. And we argue that this investigating stochasticity or randomness is an important tool for understanding the fundamental principles of biological and chemical processes. So that's what we are trying to do. So remember, I also mentioned that this is the plan overall for the course. So, and the course will consist of 3 parts. So this is within the first part, trying to understand the chemical kinetics, catalysis, and phenomenological. That's what we'll do in this lecture. Okay, so chemical kinetics. Probably most of you took classes in chemical kinetics, right? To some degree, so you know what it is. So chemical kinetics is the investigation of temporal changes for chemical reactions. Chemical kinetics people usually measure the changes in concentration of reactants and products as a function of time, and then based on this functional dependence of these changes, they are proposing what possible mechanism. They will go into detail to see some specific examples, and that's what chemical kinetics does. So schematically, this is reactants, concentration of reactants decreases, schematically concentration of products increases, right? But the devil is in detail, it's important how this decreases, how this increases, because this reflects the microscopic mechanism. Okay, so chemical kinetics. Why chemical kinetics is important? That's because what just I said it and I repeat again. The dynamics always reflects underlying. I think they interfere with each other. So the dynamics always reflect microscopic mechanisms. We will see in a simple example. That's why chemical kinetics is important. And in many cases, you are not able to get microscopic mechanism, and you only can see through dynamics. And that's why chemical kinetics is important. So macroscopic chemical kinetics. So the first paper in chemical kinetics, quantitative chemical kinetics, came in 1850, and it was written by this German scientist, he's over here. So he used acid catalyzed conversion of sucrose into mixture of fructose and glucose, and he used a very simple polarimeter, and he essentially quantitatively measured the change of concentration. So this is the reaction for those people who really want to know chemistry with sucrose. Sugar, that way, sucrose, very sweet stuff, which you all like a lot. And then goes to glucose and fructose. By the way, fructose is twice sweeter than sucrose. Maybe I should remove something. Maybe my cell phone. My cell phone. Does it help? Okay. Maybe it's my cell phone. Okay. So, by the way, this is if someone is diabetic. So usually they have this. This is okay, but not okay to have this one. Anyway, so he studied this reaction, and his question is very interesting. So his paper came out in 1850. They're interfering with each other.
2 mics are interfering.
Mics are interfering.
You said 2 mics are there.
Should I remove this? Or which one I should remove?
शायद वो इंटरफेयर कर रहा है।
अंदर की साइड करना थोड़ा ऊपर करना।
This one? And this?
ऊपर करना।
Hello. Is it better? Is better?
Yeah.
Okay, good. So Ferdinand Wilhelm was a very interesting person. So he came from a very rich family, and he studied medicine. And then his father gave him money, and he bought a pharmacy. He bought a pharmacy. He was a very successful businessman, but he was bored. He sold out the pharmacy, and he decided to do science. Okay, he never married. He married to science. He died, never married. He always liked science. And this is his paper in German. You know, before World War II, most of the scientific papers were written in German. So that's the paper. Yeah. So in this class, I don't only want to present science. I want to do a little bit. Okay, I will try not to approach this place. I will go over there. Maybe it's a phone interference. Okay. So I'd like to in this class not only talk science, but something a little bit around science. That's because this is what inspires people. People can see that scientists are also people, real people, and there are a lot of real stories over there. Okay, so we come back to chemical kinetics. So chemical kinetics quantitatively considers changes in concentration and it tries to propose mechanisms that might lead to this behavior. So let us try to look a little bit more mathematically, slightly. Suppose I have a general reaction, which I write this way: small a plus b, c, d. So a, b, small a, b, c, d equals stoichiometric coefficients, and a, capital A, B, C, D are labels for chemical reaction, compounds, for chemical compounds. So for one chemical reaction, there is only one rate. For some reason, people are confused. There's only one rate defined this way. Okay. Of course, you can have only change of one compound to another one. It might not be the same due to different stoichiometric coefficient, but strictly speaking, there is only one rate defined this way. And you can see it's positive because you're producing compound CD, and there's a sign negative because you're removing compound C and D. So people studied empirically many of these chemical reactions, and there is so first of all, clearly the reaction rate should be the function of concentration of A, B, C, D, right? So remember what I told you, that chemical reactions more microscopically is due to collisions, right? So if there is more frequent, there will be more collisions. There is a less frequent, there will be less collisions, right? And if you want to see huge number of collisions, go to Victoria Terminal in Mumbai in the morning of Monday. That will be huge number of collisions, right? The more people, more collisions. So obviously collisions proportional to concentration. So rates are the function of concentration. So generally this rate laws are not known, but based on empirical observation, people notice that this rate typically is a power law. It's a product of concentration into some powers. So this prefactor is called rate constant. You can think about it as a rate when all concentration is unity. And then there is exponent, m, n, or p. And the important things to remember, so this m, n, and p is known as the order of reaction with respect to compound A, B, C, or D. And it is interesting, so generally speaking, these exponents here are not the same as the corresponding stoichiometric coefficient.
So this is true only for the chemical reaction.
No, it's true generally. Yeah, there are situations when they are the same. But what is interesting, important to all discussions, when they're not the same, this is a sign of more complex reaction. You have to understand when chemists draw a reaction like this, it's a black box. In reality, there are many more microscopic phenomena taking place, and this is the overall result. Okay, so and this set of microscopic reactions is the mechanism. So if you have something like this is a sign of complex mechanism. Okay, good. So let's try to consider. We will consider several chemical reactions, very simple chemical reactions, just to see what information you can get. So the simplest possible reaction is known as the first order reaction. Suppose compound A goes into compound B. So then it's very easy in this case. You just write reaction rate, it's a change of concentration of A, and it's given minus Ka. That's why the order of 1, first order, the exponent here is 1. It's easy to solve this. You can easily solve this, and that gives you this exponential dependence. So A0 is the concentration of compound A times 0. It's not only chemistry, radioactive decay follows the same law. So it's exponential decay. And the results of this plotted over here. See, it's a normalized concentration. This is the result of solving this equation for some specific rate. Here, for first order chemical reaction, there are 2 time scales. They're closely related to each other, but there are 2 time scales. So more widely used concept of half-life. It's essentially this one. So and it's defined very easily. This is the time over which initial concentration of compound decreases to 50%. So it's a half-life. It's a time over which it decreases over 50%, and that's given by this formula. But there is another time scale which is sometimes called lifetime. It's time when the concentration decreases E times, E number. So you can go into another chemical reaction. For example, second order reaction, suppose A plus A2 molecules collide or do something, and you create another product B. Again, you can do the same way. You can try to solve it. The power will be here too. That's why it's second order reaction. Again, you can solve it. This is solution in this way, and you can define a half-life, again, time over which the concentration goes to 50%, and given with this expression. Please note, importantly, here there is dependence on initial concentration. Now, so I have first order reaction, second order reaction. In all cases, the concentration of compound A original reactants goes down. How can I distinguish the first order or second order reaction? And this theoretical analysis allows me to do it. So if first order, this is exponential decay. If it's the second order, it's inverse power decay, right? And half-life are different. Different half-lives. And it's better to understand this to look at the graph instead of the formula. So this is, again, the concentration is a function of time. And so let's look first. The experimental measurements for first order reaction is blue one. For the first order reaction is the green one, okay? Then how I can distinguish? So in most cases, you will see some decay. How to do it? Well, it's easy actually, because the solution that we said that we did it before, this one over there, it says the half-life for first order reaction, no dependence on initial concentration. Here will be dependence on concentration. So it means if it's first order, if I every time go time before 50%, this is the time. Time 50% after this one. You see, it's always the same time. It's always the same time to go from 1 to 1/2 to 1/4 to 1/8, right? That's the first order reaction. But that's not the case for second order reaction. You see, so for second order reaction, look at the red one. This is to go to 1/2, then to go to 1/4 will be longer, and to go to 1/8 will be even longer, right? Because of this formula. Okay. So important lesson here is from chemical kinetics, from quantitative measurement, you can actually understand something. You can say something about the mechanism, right? If you have the data and you can analyze the data this way, of course, I give you a very primitive example, but at least you can distinguish first order versus second order. So you're getting important microscopic information about underlying process without doing, in some sense, any microscopic study. Okay, so that's why chemical kinetics is important. Macroscopic chemical kinetics. You see, this is a macroscopic description, but I'm getting microscopic information. So let's do a little bit more complicated things. So, yeah.
Could you go back a slide or two, please? So you were saying that you often look at this data and then try and propose what the underlying mechanism is. So the equation you had small a capital A plus small b capital B gives small c.
This is simple. In this case, I even simplified further. Okay. So if I have this reaction or this reaction. Okay, and then if experiments are done in all cases, there will be decay, but you cannot distinguish exponential decay versus parallel decay. You cannot. Very difficult. But doing this, for example, measurement for lifetime, you can do this thing.
So when you say mechanisms, would it be something like that? A plus B gives some product.
Yeah, it's over there. And there's actually an important point to say. So chemical kinetics never proves mechanism. It's if it only says that if it agrees with the data, it means the data consistent with the mechanism. But chemical kinetics can disprove mechanism. So you can say something wrong, but you cannot say this is right. It's saying it's consistent because the complexity of science is size and other things can also describe the data. Okay. But remember, we can always disprove something, but you cannot say something is proven. It's consistent. Anyway, let's go to a little bit more complicated story. So here, I'm playing Lego, you understand, right? I start to build up from few things, so then eventually, when people do real experiments, they will collect it and use this on the Lego. Anyway, so let's have a more complicated reaction. A goes to B or A goes to C. This is known as a parallel chemical reaction. Again, you can do the same analysis. So you can write equation. Okay, so this is rate K1, this is rate K2. So this is the change of concentration of A. You can write equation like this. This is the change of concentration of B. You're building up with rate K1, A. You're building up with rate K2. You can solve this. It's a little bit more complicated, but not significantly. So again, you have exponential decay for compound A, but the overall rate constant is combined. You have a exponential build-up for B, exponential build-up for C, with the same exponent, but with a different prefactor. And let me show you the additional what you can do with this reaction. So for example, this reaction has very interesting property. Suppose you can simultaneously monitor compound B and compound C. Suppose you simultaneously. The ratio of these two compounds at any time is independent of time, known as the Branshaw ratio. This comes from this solution. If you divide B of T over C of T, this stuff is always the same. It's only the this is different. So if you have some process and two products come out, and if you simultaneously monitoring two products, and you look at the ratio, and if it's constant, that's a sign that this might be consistent with a parallel reaction. Another indication how you can get quantitative analysis from chemical kinetics to get something microscopic. Okay? And another important thing here that characteristic time scale for the system is inverse over the sum of this rate, K1 over K2. This is a little bit unusual because let's think about it. You're making compound B with rate K1, you're making compound C with rate K2. But look, the overall time of approaching your finite concentration is the sum of those. So in principle, these two completely independent reactions, right? How YC should know about this? Okay, so anyway. So let's go to another chemical reactions, consecutive chemical reactions. Suppose A goes to B, B goes to C. Again, the rate K1, rate K2. Again, you can solve it. And by the way, this is not the same as a parallel reaction rate. It's not the same as this one. It's not. You can solve it. And probably easiest thing is to look at the graph. So the compound A is exponentially decreasing. Compound B first increasing, then decreasing. And compound C is always increasing. So that's a solution of this chemical kinetic system here. And frequently in chemistry, if you ever took chemical kinetic course, did any one of you took chemical kinetic course? Can you raise your hand so I can see? Good, at least one. So what chemists do, they don't really like to solve differential equations. They really don't. So what they do, so let's assume that this intermediate is very reactive, which means that this rate of making B is quite fast. Then you can do this approximation, and it works reasonably well. And this picture done for this situation. So you see, you can really approximate that B is more or less constant, slowly changing. The steady state approximation, and it's actually very powerful. Many mechanism, if you look at chemical kinetics, many mechanisms people determine this way. Okay, so let's go probably to the last chemical reaction that we will look at. Last simplest one is reversible chemical reaction. This is more realistic description because in the nature there is no irreversible things. Everything is reversible. So A goes to B, B goes to A. Again, you can write equations like this, right? So you're creating compound B with this rate, you're removing compound B with this rate. You can solve this equation eventually, and you can reach effective equilibrium. So at the end, the system will reach an equilibrium at which the amount of created B is equal to amount of created A, and here it's convenient to talk about something which is known as the principle of detailed balance. So the system will reach equilibrium only if every microscopic transition in your system is in equilibrium. That's the principle of detailed balance, which means that for every elementary chemical step, rates in opposite directions are balanced each other. Okay, good. So this is solving this for this reversible reaction, and you can see again there is exponential approach to equilibrium with a time scale again, which is the sum of forward rate and backward rate. Again, doing the very simple calculation, you can get microscopic information about the system. Good. Now, another important component for chemical reactions is dependence on the temperature. Chemical reactions depend on temperature. We know this thing, right? We saw it this morning when I light candle, right? It didn't. You need to have some local increased temperature ignited to do it, right? So chemical reactions are typically faster with higher temperature, and the very famous expression, which is phenological expression, comes with associated with the name of the Swedish scientist Svante Arrhenius. This is called Arrhenius law, and this how the rate of chemical reaction depends on the temperature. And we found empirically and theories of chemical kinetics actually has some justification for this. And this is known as the activation barrier. So it's one barrier. Yeah. So the most important thing that when you use this, when you cook, we cook food, so the chemical reactions are happening faster for one that you needed to eat it, right? So this is a scale of something. Okay. So my apologies against American picture, that's why it's Fahrenheit. But you know how do you know how to change Fahrenheit to Celsius? Easy, right? Easiest thing is divide by 2. It's harder one, minus 32 times 5/9. Anyway, easy. If you live in America, it's immediately you can do it. So cooking is an example when temperature affects chemical reactions because you need to do something faster. Good. Svante Arrhenius actually was a very interesting person. He, strictly speaking, he is a founder of modern chemical kinetics. He actually was the first Swedish Nobel Prize. So remember Nobel, the name of the prize comes from Alfred Nobel. From which country he was? Right. What he made money on? Part of it. Other part of it was made on oil in Russia. In Baku, in Azerbaijan. So this actually is a family. There are several brothers. So the part of the money was made in Russia on oil. He lived a significant part of his life in Russia also. Anyway, so Svante Arrhenius was the first Swedish Nobel Prize winner. There's an interesting story about him. He learned to read himself when he was 3. And he learned to count himself looking at his father. His father was a land surveyor. So, there was a person who measures land. So he did his PhD on conductivity of electrolytes, and this eventually earned him Nobel Prize. But when he defended, he almost failed. The professor didn't like it. It was at Uppsala University. They thought it was a disaster. They want to fail him, and only they wanted to save, just to be nice to him. They gave him. So in Sweden, those times they were given grade 1, grade 2, grade 3, grade 4. The grade 4, he was given grade 4, the lowest possible grade. So yeah. So there is no profit in your country, as you can see. And he got Nobel Prize for this. So if you're brilliant students, you can do something, you can get Nobel Prize eventually. Yeah. So Svante Arrhenius did a lot of things. So of course we know Arrhenius law, but there is one more important thing for us, is that he experimentally proved that chemical reactions are the same in living system and in test tubes. There was misconception. People thought chemical reactions are inside of living system, outside not the same, and he proved quantitatively that they are the same. That's why I'm saying that biology to a large degree is chemistry. Okay, so this is an example of real experimental example of Arrhenius dependence. And again, you see, we typically, when people analyze experiments, you probably you took the classes, they tell you do linearize, right, in linear coordinates because it's easier to do it. Yeah, so in linear coordinates, this is how this logarithm of rate depends on linear on inverse temperature. This is real experimental data for this reaction for chlorine oxide. It goes into chlorine to this horrible reaction. You can only do it under the hood. But that's dangerous reaction. But that's what was measured. And you can see that the points are really nicely follow a linear plot, and you can get estimates of activation energy. And this is the phi of the graph. Okay, so it's very powerful. People use it. Arrhenius works amazingly well in many situations. Good. So let us talk about something else related is the catalysis. So catalysis is an extremely important concept. We will have one more lecture where we'll talk a little bit more catalysis. But catalysis is a unique physical-chemical phenomenon when you add some compound to your chemical reaction. Suppose you have chemical reaction with slow. You add something to your system and the reaction goes faster. And the compound itself is not consumed. So schematically, so you can think about chemical reaction which is slow, like overcoming the mountain, but catalysis provides some additional pathway on whatever which you can do. So catalysis is associated with another Swedish scientist, Jöns Jakob Berzelius. He actually coined the term catalysis, and he studied this catalysis, but he was actually thinking it's purely physics, electric thing. That's what he thought. That's not what we think right now. The first enzyme, biological catalysis, was discovered in 1983. So for catalysts which are biological origin, there is a name of enzyme, as you know, and the first of them was studied by this French scientist GIAN and Perso. And this reaction, the first reaction that they studied, is the reaction of transformation of starch into sugar. And for all of us who can breakfast, that's what's happening right now. Amylase is enzyme which is in our saliva. So we eat food, right? And we need to transform starch into carbohydrates, which are easier than to transform into water and provide energy. So this is amylase, this enzyme does it, and this is the food which has a lot of starch. Essentially, it's a digestive enzyme. It's a digestive enzyme. So what is interesting is that some people has a disease when there's not so much of this enzyme, and you can actually buy. I don't know if you can buy it in India, but at some pharmacies you can buy this amylase. Yes. Good. So Berzelius also was an interesting person. So he is considered the founder of modern chemistry. The way we know chemistry comes from him, from Berzelius. He probably is the last person who knew all chemistry, but it was not so much in 20 years, 200 years ago. He knew all the chemistry, from organic to whatever. He was actually a very interesting person. He was actively promoting complete abstinence from alcohol, almost like Narendra Modi. No alcohol. He was thinking that this is bad. Yeah. The most important contribution that he made to science was chemical notation. So he is the person who had these notations. That was him. Okay. So the only difference, this is H2O water that we do it now. The only thing that he did, he said it like this. Mathematician didn't like it because this is a square or whatever. So essentially, yeah. So but that significantly simplified things. So the chemical notations that he introduced. He actually also discovered two new chemical elements. One is the cerium, another one is selenium. As I see, he did everything possible things in organic chemistry those times. And for us, he was the first to argue he was the first definition what is organic compound versus inorganic compound. So anyway, Berzelius was a very smart person. Good. Catalysis. So we currently understand catalysis. So catalysis is, it doesn't change free energies of initial reactants or products, it just creates a different pathway. And this picture is shown. Okay, so this is typical picture that you can find in textbook. This is the reaction coordinates, kind of imaginary path of your reaction. This is energetic scale. So let's say the original solid black reaction is slow, that's because the barrier is high. But the catalysis provides a different pathway. Okay, different pathway, maybe there will be two mountains, but each of them is easier, and the result reaction is faster. Reaction is faster. So there is important observation about catalysis. There is still a lot of misconception. So catalysts do not change initial and final initial components and final components to free energy. So because of this, catalysis accelerate both forward and backward reaction. Okay, but because you typically apply it for the system where the products anyway much lower in energy, you effectively see that they go into this direction. There are also catalysts which can slow down the reaction, inhibitors. Okay, so that's what we have to remember. Okay, good. So let us go to enzyme processes. So remember, enzymes are biological catalysts. Let's consider this reaction that we actually mentioned this morning, hydrogen peroxide, right? So if you go in the pharmacy, buy it, and you put it a little bit, yeah, you can see there is a fluid and there is a little bubbles come slowly. The reaction is relatively slow at room temperature, but you can accelerate this reaction. I don't know if you did experiments when I was a chemist in Moscow, we had this experiments. What you did, you take hydrogen peroxide and then you drop just one drop of potassium bromide. And then it was like, so the reaction accelerated 10,000 times by adding bromide. Iodide is also good, but not as fast, but bromide is really fast. But there is a special enzyme which does it. The enzyme is called catalase, and the reaction 10 times, 15 times faster. So comparison with this simple reaction. So you see? So what we can see from this example that biological catalysts are very extremely efficient. They're very selective, very efficient, and scientists propose this idea, the mechanism of enzyme mechanism so-called follows lock and key concept, which probably some of you heard. These biological molecules are creating the active sites for reaction is happening. They're very specific in geometry. So if you want to change the substrate, only this substrate can fit, and you can make a product. Okay. For this reason, the number of enzymes is huge. So, for example, one of the most important functions in biological system is to phosphorylate or dephosphorylate. So we know at least 500 different so-called kinases which do only phosphorylation, but for different substrates. Okay. So biological enzymes are very selective, extremely selective, right? Essentially, they can work only for one specific reaction or one specific substrate. The nature did it this way. The nature did it this way. The nature need to have this to be very specific, and you need very low amounts of enzymes are needed then, and then universal chemical properties to describe all this enzyme. Okay. And we go to this universal mechanism, which is very famous, Michaelis-Menten mechanism, which is more than 100 years old. So more than 100 years old, in 1913, two scientists, Michaelis and Menten, they uncovered the most used, this is the most probably cited paper in zoology or in biological things, is Michaelis-Menten. So they found that the chemical reaction for enzymes typically follows the parabolic ways. This is Leonor Michaelis. He was a German-American scientist. This is Maud Menten. She was Canadian-American scientist. Also, very interesting people. So Leonor Michaelis, he was born in middle-class Jewish family in Germany. He wanted to be doctor first, but then thought no, he liked to do science. There's an interesting story. So in the beginning of crooks were always in the beginning of 20th century, 21st. So the beginning of 20th century was a German scientist who was a crook. He said he claims that he has a test on pregnancy. All you need to do is blood. So this Michaelis actually looked at his test and said this is fake, but Michaelis was Jewish, this person was German, so people didn't like him, he was kind of discriminated. In fact, he had to leave from Germany to USA in 1926, but that saved his life. Otherwise, he would stay in Germany, he would be killed. And he did quite well in the United States. Probably girls would appreciate it. He is the one responsible for the fact that you can actually change your hair easily. Because he discovered that this type of glycolic acid could dissolve keratin. Keratin is one of the main proteins in hair. So if you do it, you can do whatever you want with your hair. Okay, so all this product for hair, what you buy, you're using Michaelis discovery. So that's why I call him German American, because a lot of times he actually spent in America. The company Max Factor, which cosmetic factory, was come out after this discovery. Anyway, Maud Benton, another very interesting person. So she was the first woman in Canada, pure medical degree, the first one. Okay, but in those times, women were not allowed to do research in Canada. So she actually went to Germany and worked with Michaelis. That's how it worked. That's how they come out with joint paper. She obtained her PhD in biochemistry from the University of Chicago, but could not get any jobs in Canada. Women were not allowed to do anything. So she worked as a doctor and research professor at the University of Pittsburgh in the USA. She was known for knowing 6 languages, that I mentioned: Russian, English, Italian, German, French, in one of the native tribes. So she was an interesting person. Good. So Michaelis Menten, let's try to go a little bit more on Michaelis Menten. You probably have seen this Michaelis Menten, let me try to repeat it. So the idea of Michaelis Menten mechanism is that E is enzyme as the substrate. You create an intermediate ES compound, and it's reversible, and then from this one you create final product. And if you can solve for what I told you before for reaction rate, you will get an expression like this, where maximum speed is, this is maximal reaction speed, when we have a lot of substrate, and there is an important constant appears, which is known as the Michaelis constant. For some reason, it's called Michaelis constant. All the mechanism is called Michaelis Menten. Constant is called Michaelis. I don't know. Probably. Anyway. So E0 and S0 are initial concentration of enzyme, and this explains this parabolic dependence. So when the concentration of S is small, you have a linear dependence. When it's large, you actually saturate. That's correct. Again, in practical applications, people typically try to linearize these things, and they use something. So this is known as the Lange-Burke equation. It's the same equation, but made so that inverse rate, inverse concentration of substrate, you can plot it. This is, by the way, some of the real data. That's how they plot it. And from this data, you can determine all we need: maximal rate, Michaelis Menten constant, and so on. Michaelis constant. Okay, but Michaelis Menten mechanism is powerful enough because you can extend it. So, for example, you can extend it and include so-called competitive inhibition. Competitive inhibition means that there is another compound called I, which can bind to enzyme and essentially block enzyme from doing its main catalytical part. Again, you can do the same calculations as I told you, right? And you can get the formula, final formulas, and you see this, there's additional factor due to this inhibitor. Or you can do something which is known as a non-competitive inhibition. Suppose this compound not only reacts with enzyme, but also reacts with this intermediate. Again, you can do the mathematics and you can get the expression here. And it's always convenient to look at the graphs. So this graph shows you normalized reaction rate. So the solid line is a pure original Michaelis Menten. You can see what I told you, right? When small concentration of enzyme is linear, when large it saturates, that parabolic dependence. So competitive inhibition is inhibition, let me remind you. This is a competitive inhibition when you compound only affects enzyme. Competitive inhibition will eventually reach the same maximal rate, but the difference with pure Michaelis Menten that it's slower, it takes longer, but otherwise will reach it. And there is a non-competitive inhibition when this inhibitor binds here as well as here, both have a different dependence. Again, the only reason I show this picture to show that just looking at the graph and assuming some model, some mechanism, you can say something about the system. Okay? So suppose you have Macroscopic, this is the dependence. Suppose you had some compound inhibitor, and if it follows this picture, that it's that it can only bind to enzyme, but if it follows this, it binds both to enzyme as well as to intermediate state. Again, you see there's from this relatively simple quantitative arguments you can get some information on mechanism. Okay, that's what I'm trying to show. Okay, so this is the end of the lecture. So we talked about kinetics and catalysis. Again, in a very primitive, very simple way. My main message was this chemical kinetics with extensions provide some quantitative description, which you can apply for getting some information, microscopic information. You can distinguish between several things, and this is it. Okay, so ask any questions. You can come back if needed. Was it too much chemistry here? Chemical kinetics is something that physicists should take, definitely. I don't know about mathematics people, but physicists should. Yes?
This is something you had mentioned at the beginning. You said you can use chemical kinetics to get the mechanism.
You can use chemical kinetics to in principle, chemical kinetics should reflect microscopic mechanism.
Is the microscopic mechanism the thing that you do, the balanced equations that you learn?
No, it's even more detailed. But even more detailed, I could. So, for example, if I would look at this reaction, okay, this is the overall reaction H2O plus O2. If you start to look in more detail, it's quite a complicated thing. There's a lot of transitions like this. H2O2 can go to 2OH, H2O2 can go to H2O2 plus H. There's all these species are experimentally proven. Okay? What you see overall is a chemical reaction is a black box. There is a lot of more complicated processes taking place. Okay. Yes.
Sir, in many of the mathematical models, I have seen like cell interaction models, like in cancer, and also in infectious disease models. I've seen like many of the researchers, they are using this term Michaelis Menten type reaction terms.
Yeah.
So this basically comes from enzyme reaction.
Right.
So can we take it to like cell interaction?
Okay, so let me explain. So they argue, these people argue that there is an enzyme which does something, right? I don't know the reaction of this enzyme, of this reaction rate, but given the fact that so many enzymatic reactions follow Macroscopic, let's assume it's Macroscopic. Means it assumes it's dependent. This one shown over here. That's what they say by Macroscopic. Okay. That's what the typical things what they say.
In some of the models, they directly take it like directly proportional to the concentration. Whereas in some other models, they have considered this kind of.
Yeah, so, and it could be that both of them right and both of them wrong. Because, as I mentioned here, so let's go to this graph. If you are in a regime when substrate is very little, it's really linear. Concentration of substrate is linear. But it could be so other situation substrate is not, concentration of substrate is not small, and then you have to take the whole thing into account. Okay? So probably they have additional information which allows them to say it was just linear or a little bit more complicated. So Michaelis Menten is nothing else as an assumption that there is one intermediate state before you're making the product. That's it.
If you have like the reaction rate for these sub reactions, so can we find out the?
Yes, that's exactly how people determine some of the mechanisms. You can write it down and combine all of them, and you will get eventually. But so if you remember, so if I, at the beginning I mentioned rate is up. Go over 1 second. Beginning 1 second. Here, right? So if I take into account all of the things here, then I will be eventually able to determine this parameter. And that's known. And in some cases, it's even not integer. This, by the way, this should not be integer. The number, these, always A, B, C, D, always integer, but this number M, N, O, P is not integer, could be square root, could be 1/3. And that's a reflection of mechanism. There's a theory of chemical kinetics. If you're interested, I can give you a lecture on this. I'm not sure you need it. So chemical reaction, when we write it, it's a black box. There's a lot of more microscopic reactions happening, and the overall reaction rate is the reflection of this mechanism. Any more questions? Yes, please.
So how is the reaction speed or the mechanism maintained constant? Like varies if we are doing the non-competitive inhibition. Like because of in a competitive inhibition, you know that it will decrease.
Yeah. So the formula spells you the thing. So let's go to the formula. You don't need to remember this, but there is a formula which spells you this. So this is in original, right? Original simple comparison method. If you go to just so if you go to this, this is competitive one, right? So competitive, you can see that if you increase this to infinity, right, your maximal speed is still the max, right? Because the whole thing will go away, right? That's the reason in competitive inhibition, you eventually will reach the same final point. It's like Mercedes or Tata, you will eventually drive to the same final point. But here, this formula here shows you that effectively Km is Km multiplied by this fact. Okay, if you increase the concentration to infinity, right, you will not reach the rate Vmax. You will reach rate Vmax divided over this fact. Okay, so that's the reason. And that shows up over here. Competitive, you reach the same thing, but slower. Non-competitive, you don't reach the same level of reaction. Okay. So you should not worry about this is a lot of chemistry. All these things is done only to illustrate one point. Looking at the dynamics can tell you something about underlying microscopic mechanism. That's it. And this is just an example of it. And this, okay?
For example, if any mechanism is happening having the intermediate steps, okay?
Yeah.
Like for example, K1, K2, Can we talk about the average rates also in terms of?
Yeah, we always can do, because there's always time to go from initial to final. We can always talk about rates. So the rates are inverse of mean time, or people mention inverse of mean first passage time to go from initial to final. You can always talk about it. Okay, so next time when you eat some things, or rather, remember that amylase is converting corn into starch into sucrose. Thank you. Good. Thank you. Okay, we're done, right? Thank you. Feel free to ask me if you want one-on-one question.
Easily we can have the innovative.
Was it too much chemistry? Right?